In this fast-paced world, artificial intelligence is everywhere, seamlessly integrated into our daily lives. At the heart of this transformation is deep learning, a powerful technology driving innovation. Deep learning empowers machines to learn and decide by processing vast amount of data. It's a breakthrough that enables AI to recognize patterns, understand language, and evolve over time. Inspired by the human brain, neural networks are the backbone of deep learning. They analyze data layer by layer, extracting complexities once thought exclusive to human cognition. From personalized recommendations to medical diagnostics, deep learning is revolutionizing industries, making our lives more efficient and connected. In just a minute, we've glimpsed the power of deep learning, the force propelling AI into every corner of our lives. It's not just technology, it's the future unfolding before our eyes. If you've played around with training a neural network before, you know there are many settings to get things just right. And that's what this series is all about. We are going to learn 40 techniques and tricks for deep learning to make it work better, smoother, and just plain amazing. From tweaking things to clever improvements, join us on this journey to make deep learning as good as it can be. We'll use PyTorch as our main tool to build everything from scratch. We'll kick off right from the fundamentals and gradually delve into advanced topics. Throughout the journey, we'll cover optimization and training strategies, ways to speed things up, and how to keep an eye on what's happening. We'll also touch on evaluation methods, domain adaptation, and explore some often missed but crucial techniques. So come along and be part of this learning adventure. Before delving into the coding process, it's crucial to install Anaconda. To begin, open your browser and enter Anaconda in the search bar. Look for the first link that directs you to anaconda.org and click on it. Once the website is open, locate the download button, click on it, and depending upon your operating system, the corresponding version will be initiated for download. In my case, I'm using a Windows system, so the download is in progress for the Windows version. After the download is complete, it's time to proceed with the installation. In most cases, you can simply click next and allow the installation to proceed with the default settings. However, it's important to ensure that you select the Add to Path option during the installation process. Click next to confirm your selections and the installation will commence. And that's it. The installation is now in progress. And once you're done, I want you to open an Anaconda terminal and follow the steps. In the video description link, you can locate a requirements.txt file, download it, and proceed by executing the following commands. Begin by creating an environment and allowing you the flexibility to pick any name you prefer. Activate the newly created environment and then proceed with the final command to install all the dependencies specified in the requirements.txt file. After the installation is successfully completed, launch Jupyter Notebook from your terminal. It should automatically open in your browser. Click on New, choose Python 3 Notebook, and now we're all set to commence our coding. Let's rename the notebook to Baseline Notebook and let's begin. Let's quickly check if PyTorch is installed correctly. Import it in a Jupyter Notebook cell, and if there are no errors, we are ready to proceed. First, we import essential PyTorch and Torch Vision libraries. Torch for core functionalities, Torch Vision for dataset utilities, and torch.nn for building neural networks. We also include torch.optim for optimization. Next, we import MNIST dataset from torchvision.datasets, an iconic collection of handwritten digits for image classification. For image processing, we use torchvision.transforms to prepare data for our neural network. Moving on, the data loader class from torch.utils.data efficiently loads and iterates through data batches during training. Lastly, matplotlib.pyplot is included for potential visualization, useful for analyzing model performance with graphs and images. Here we are setting up the MNIST dataset for training and testing. For the training set, we use the MNIST class from torchvision.datasets, specifying the download path, applying a series of transformations such as resizing images to 32 x 32 pixels and converting them to tensors. Similarly, for the testing set, we create another instance of MNIST class. This time, we set train to false to get the testing data. Again, we apply the same set of transformation to maintain consistency in data processing. Both datasets are now ready for training and evaluation with the specified transformations. This ensures uniformity in the input data fed into our neural network. Upon executing this code cell, the dataset will be fetched from the internet and saved to the designated path. Here we're using matplotlib.pyplot to visualize a grid of 25 images from the training dataset. We set up a 5 by 5 grid using plt.subplot and iterate through the first 25 samples in the training data. For each image, we remove axis sticks, we remove the grids, and display it using plt.imshow after converting it from PyTorch tensor format to a NumPy array. The CMap is equal to plt.cm.binary ensures a black and white color map for better visibility. We also displayed the corresponding label as X label. This gives a quick peek into the dataset showcasing handwritten digits and their associated labels. This will be subplot, now subplots, and upon rerunning the cell, you will observe that the dataset contains handwritten text ranging from 0 to 9, and our objective is to classify this handwritten text. This visualization helps us understand the data distribution and aids in debugging and analysis. Now we are creating data loader instances for our training and testing datasets. Data loader is a PyTorch utility that helps efficiently load and iterate through data during training. For the training data loader, we use data train and specify the batch size using batch size and enable shuffling of data with shuffle equals true. Shuffling is beneficial for introducing randomness and preventing the model from learning the order of the data. Similarly, for the test data loader, we use the data test and set the batch size. Shuffling is not necessary for the test data as we typically evaluate the model on ordered batches. These data loader instances will play a crucial role in training and evaluating our neural network by providing batches of data for each iteration. Now let's set up our neural network for training. We'll determine the device using toss.device CUDA if toss.CUDA is available, or else we'll stick to CPU. This flexibility allows us to leverage the power of GPUs if available, enhancing training speed significantly. Next, we create our neural network using nn.sequential API. It's a simple architecture with three fully connected layers, each followed by a ReLU activation function. The input size is 1024, leading to 512, then 256, and finally 10 output nodes representing the digit classes in our case. We move the entire model to the specified device using toDevice and ensuring computations occur on the GPU if available. Moving forward, we define the loss function using nn.crossEntropyLoss, a suitable choice for classification tasks dealing with multiple classes. For optimization, we employ the Adam optimizer with optim.adam model.parameters. This optimizer adapts learning rates for each parameter, often leading to more effective training. With these components in place, our neural network is ready for training on the MNIST dataset. Now let's take a closer look at our training function. This function named train takes epoch as an argument and is responsible for training our neural network for a given number of epochs. Inside the function, we set the model to training mode using model.train. We then iterate through the training data using a for loop over train data loader. For each batch, we move the input images and labels to the specified device, that is either GPU or CPU, and flatten the images using images.view, images.shape0, -1. Let's examine a sample of our data. The shape is 128, 1, 32, 32, where 128 denotes the batch size, 1 signifies the number of channels, and 32 by 32 represents the height and width. When we apply the operation images.view images.shape0, -1, it essentially preserves the batch size dimension while flattening the remaining dimension into a single vector of 1024. The resulting vector serves as the input layer with 1024 neurons for our neural network. We then perform the key steps of training, zeroing out the gradients with optimizer.zeroGrad, obtaining the model predictions with output is equal to model images, calculating the loss using criterion output, labels, back propagating the gradients using loss.backward, and updating the model's parameters using optimizer.step. Throughout the training process, we collect the batch-wise losses in the loss list. After each epoch, we calculate the average loss and print it out. This function encapsulates the essential steps for training our neural network. Now let's explore our testing function named test, and we pass the epoch parameter. The function evaluates our trained model on the test dataset. Inside the function, we set the model to evaluation mode using model.eval. We initialize counters for total correct predictions and average loss. Within the nograd context, using torch.nograd, we iterate through the test dataset using test data loader. And similar to the training function, we move images and labels to the specified device, that is either CPU or GPU, flatten the images, and obtain the model parameters. We accumulate the average loss over all batches and count the total number of correct predictions, comparing them to the ground truth labels. After processing all batches, we calculate the final average loss and accuracy. The results are then printed out for each epoch. This function provides insight into how well our model generalizes to unseen data. The run function orchestrates the training and evaluation process for multiple epochs. Using a loop over the specified number of epochs, we call the train function to train our neural network on the training dataset. The training function updates the model parameters based on the optimization process. Following the training, we call the test function to evaluate our model on the test dataset. This provides us with insights into the model's performance on unseen data. The process repeats for each epoch, allowing us to observe how our model improves over time. Looking at the ongoing training process, it's evident that the model is actively learning, and this iterative training will persist for the designated number of epochs we have specified. I'll let it continue training and I'll return once the process is complete. It's been a span of 2 days since I last checked on the ongoing process, and during this interval, I encountered some challenges, including the necessity to update Jupyter due to a system crash. But now that everything is back on track, I've examined the results from the last epoch, and it's quite impressive. The model achieved a commendable accuracy of approximately 98% with a minimal loss of 0.00080. However, upon closer inspection, we can observe that there are instances during the training phase where the model exhibited even better performance. Unfortunately, the weights from those high performing moments weren't saved, and we were left with the parameters from the final epoch. In the subsequent stages, we'll explore strategies to address this issue and delve into various aspects to give you complete control over the intricate details of your neural network. And that wraps up our video. If you enjoyed it, remember to hit the subscribe button so you won't miss any future updates. If you found the information helpful, give it a thumbs up, drop a comment with your thoughts or feedback, and stay tuned for the next video. See you until next time.